Well, hi there, boys and girls. Today we're going to talk about graphing exponential functions. I almost said rational, but we're doing exponential functions. And we are going to look at what the difference is between an exponential function and a regular polynomial. An exponential function is a number to a power of x. That's backwards from a polynomial because polynomials are like x squareds. And they behave a little differently, and we're going to take a look at their graphs today. So I'm going to do this by making a table first of all, and we're going to graph it on my little graph down here. So let me grab a hold of that graph and bring it up a little bit so we can do that. All right, so let's look at our table. Our table would be, let's let x equal numbers, and then we'll see what y is. If x is 0, then I would plug 0 in for x, and I would get 2 to the 0 power. And now we learned, because we just reviewed exponents, that anything to the 0 power is 1. So that means that this graph goes through 0, 1. And you are going to want to remember that. All exponential functions will travel through the y-intercept 0, 1 as long as they haven't been moved up or down with a shift. So every exponential function is going to travel through that point because anything to the 0 power is 1. Now what about another point? How about if x is 1? If x is 1, then I'll have 2 to the first, which is, well, that's just 2. So over here at 1, I go up to 2. And then if x is 2, then y is 2 squared, which is 4. And it starts to get big here. 1, 2, 3, 4. And then, of course, if x is 3, then y would be 8. 1, 2, 3, 4, 5, 6, 7, 8. And it just explodes. It goes straight up through there. And as a matter of fact, if x is something like around, I think it's about 28 or somewhere in there. If x gets as big as 28, this y value is over 1,000,000. And so that would be hard for me to graph, so I'm not going to do that. So exponential functions actually get large very quickly. Now what I'm going to look at, though, is these ordered pairs, 1, 2, and I've got 2, 4, and I've got 3, 8. You can look at these and you can tell that the base, these y values, 1, 2, 4, and 8, those are powers of 2. And so that's why my base is 2. You can also look to the left. Now I'm going to scroll down here and talk about negative values for x. For example, if x is negative 1, that would be 2 to the negative 1 power. And again, we just reviewed this. A negative exponent means we move it to the bottom, and that would be 1/2. So at negative 1, I'm at 1/2. Now what about at negative 2? At negative 2, that would be 2 to the negative 2, which would be 1 over 2 squared, which would be 1/4. And we are getting closer and closer to the x-axis. And of course at negative 3, I've got 1/8, and so I am approaching an asymptote of the x-axis. And so this is what this little graph looks like. It hugs the x-axis until it gets to 0 and it touches at 1, and it just goes like a rocket. It just shoots up like this and gets really, really big very quickly. And to the left, it hugs the x-axis. So let's talk about a few things. Let's talk about domain. The domain for this graph is all real numbers. The reason that is because I can plug any number I want in for x. And if it's negative, it just makes a fraction. If it's positive, it makes a great big number. Now the range is not all real numbers. Something that's interesting is I cannot make this equal 0. I cannot raise 2 to any power and make it 0. I also can't make it negative. We got a negative exponent, but that didn't make a negative number. So my range was all numbers bigger than 0. I cannot make that drop below the x-axis unless, of course, I do a transformation, which I'll talk about. Now this has an asymptote, but it only has an asymptote towards negative infinity. Out here towards negative infinity on the x-axis, we have an asymptote of y equals 0. That is one of the exponential graphs, 2 to the x. Now I want to show you another one that you need to know. And this is a number e. And e is very, very important for this unit. It's very important in calculus, and I'm going to tell you what e is. Everything I know about e I learned from Andrew Jackson. And here is what e is as a number. 2.7, 1828, 1828, 45, 90, 45. And it goes on forever. It's an irrational number with a big long decimal. It's bigger than 2 but less than 3. Now, here's what the reason I said Andrew Jackson. Andrew Jackson happened to be our 7th president. He served 2 terms. He was elected in 1828. You write that number twice because he served 2 terms. Now, that's all a true statement. Now, the next part is sort of legend because it's not really true, but it's sort of cool. And the legend is that he wore 2 Colt Walker 45 pistols on each hip, and 45 plus 45 is 90. Now, that's not really true because the Colt Walker 45 didn't come out till like 1865. And so since he was president in 1828, that couldn't really be true. But still, bigger than 2, less than 3 is the number E. Now, E is used in exponential growth and decay. It's used in continuous compound interest. It's used in half-life. It shows up a lot. Now, let's take a look at this graph. E to the x will also go through 0, 1. All exponential graphs go through 0, 1. Now, when you plug in 1, however, you're going to get e to the first. So I've got my little table over here. X and y. If x is 0, y is 1. If x is 1, what is y? Well, it's e to the first, which is this number right here, 2.7 blah, blah, blah. I'm just going to keep it e to the first. So at 1, it's bigger than 2, but a little less than 3. I'm going to call that ordered pair 1, comma, e. And then if x is 2, I get e squared. Now, e squared has got to be less than 9, but bigger than 4. So out here at 2, 1, 2, 3, 4, 5, 6. It's less than 9. I'm just going to guess somewhere up there. But I'm going to call the ordered pair 1, comma, e squared. It has the exact same behavior towards the left as the previous exponential function that we did. If x is negative 1, I get e to the negative 1, which is 1 over e, which is 1 over that number, which is, it's a fraction. So I still get the exact same kind of behavior. But the reason you're going to know the difference between this graph and like 2 to the x is the y values. Those y values are bases of e. Earlier, my y values were bases of 2. I still have the same answers. The domain is all real numbers. The range is y is greater than 0. The horizontal asymptote is also y equals 0. Now, the only other thing that I'm going to show you is how to change some of these. So I'm going to have you look at one more graph here, and I'm going to show you what happens. I'm going to use e as some examples. We're going to graph e to the negative x, and we're going to graph 2 plus e to the x. And then we're going to graph, I guess, negative e to the x. I'm going to show you what happens. As a matter of fact, I should probably do these in different colors. I'm going to do these in different colors. So we're going to have this one in blue, and then we'll do this one. We'll do that one in green. Okay, so here we go. E to the negative x is going to look like this. It's still going to go through, I want this one in black. It's still going to go through 0, 1. Instead of a horizontal asymptote to the left and then exploding up, this does the reverse. This is a reflection across the y-axis. So that is going to look like this. Horizontal asymptote out to the right this time, and then it does this great big rocket explosion towards the left. So there is e to the negative x. Now let's graph 2 plus e to the x. This is simply a shift of up 2. E to the x up 2. Now this one won't go through 0, 1. This one will go through 0, 3. The horizontal asymptote will no longer be y equals 0. It will be y equals 2. So that's where it's going to hug. And it's still going to be this exponential graph hugging its asymptote and then shooting up like that. So that's sort of messy, but that is 2 plus e to the x. You took the e to the x and you shifted everything up 2. Now let's graph negative e to the x. This is going to be a reflection across the x-axis. So I'm going to, instead of going through 0, 1, this is going to go through 0, negative 1. And it's going to look like this. Shoot straight down like a rocket going down. So those are typical transformations that you should remember, and you're going to be graphing these tomorrow in class. And just remember, exponential functions basically look like they hug the x-axis and they shoot up like a little rocket, and they get big really, really fast. And you can figure out the base by looking at those y values. And I think that's it, so I will see you guys tomorrow.